Here's solutions for some problems from Chapter 10. Numbers 1, 3, 9, 11, 23, and 25. Introduction to doing problems with rotational variables. So, number 1. Good baseball pitcher can throw a baseball toward home plate at 85 miles an hour. With a spin of 1,800 revolutions per minute. How many revolutions does the baseball make on its way to home plate? And for simplicity, assume that the path 60 feet in a straight line. So it's going to travel 60 feet at that speed. You could work with these units and try to do your best there, change miles to feet and that sort of thing. But we have a lot of different units here, right? I've got miles, feet, hours, minutes, revolutions. So I think I'm going to go ahead and turn everything into SI units. So let's do some conversions. So first of all, the speed, which is 85 miles in 1 hour. This is good practice, right? Make sure we still are happy about this. I'm going to get rid of miles and turn that into meters. I'm just going to turn everything into SI units. It's not absolutely necessary to do that, but that's the way I'm going to do it. And then 1 hour is 3,600 seconds. So 85 times 1609 and divided by 3,600 is about 38 meters per second. Right? 60 feet. From feet to meters, you could look up a conversion there, but if you just remember other things, you know that there are 5,280 feet in a mile and 1,609 meters in a mile. So that's a conversion factor right there. So 60 times 1,609 divided by 5,280. At 18.3 meters, right? We thought it was about a 3-to-1 conversion, more or less. And then I have 1,800 revolutions per minute. And since they're asking about revolutions here, I'm just going to turn that into revolutions per second. So I just need to get rid of the minutes. 1 minute is 60 seconds. So that's equal to, what would that be, 300 revolutions per second. And just so in case, well, we will have to do this in future problems. I don't need it in this problem because the final answer they're asking for how many revolutions. But here, just so we can see how to do this, if you have revolutions per whatever and you want to turn it into an angular velocity, and that means you would want to turn it into radians per second. So to do that, you would say, well, 1 revolution is 2 pi radians. That's the conversion factor for that. So that would be 600 pi radians per second. So if you wanted to find the omega in this problem, that's how you would do it. We don't need it in this problem because, again, the final answer they're asking for how many revolutions. All right. So just to finish this up now, it should be pretty easy. I've got the, since we're just assuming that this is going at a constant velocity from the pitcher to home plate in a straight line, that means that since velocity is equal to displacement over time. When you have a constant velocity, that means time is equal to the displacement over the velocity, so that's 18.3 meters divided by 38 meters per second. Which is about 0.48 seconds. And I'm going this many revolutions per second. So the number of revolutions is equal to 300 revolutions per second times how many seconds we're doing it for. Right? So that gives me 300 times 8, 144 revolutions. If you did that in a different way and you got the right answer, then that's fine. I just decided to convert everything to SI units, so that's not the only way to do that. But that's what seemed like the right thing to do to me. That's what I did. Always trying to do the right thing. When a slice of buttered toast is accidentally pushed off the edge of a counter, it rotates as it falls. If the distance to the floor is 76 centimeters, and I suppose if we take down to be negative, then that delta y would be negative, right, if it's going to fall that far. And for rotation less than 1 revolution, what are the smallest and largest angular speeds that cause the toast to hit and then topple to be butter side down? So if this is the toast with the butter on it this way, and we're going to fall, if it's going to land butter side down, then I think the minimum would be a rotation of 90 degrees, right? If it was that, then it would just barely land on this edge and topple over this way. And then the maximum would be if it went all the way to 270 degrees, right? So it didn't quite make it over so that it flipped over butter side up. So I think that we're talking about from 90 degrees of rotation and 270 degrees of rotation. So I hope that makes sense, right? Those are the conditions where it will land butter side down, which it usually does, if you have any experience with this particular situation. All right, so rotation less than, so we're not worried about it like flipping around lots of times and landing like this, just for less than 1 revolution. So they want to know smallest and largest angular speeds that cause the toast to hit and then topple to be butter side down. So here it's going to go 90 degrees in however much time it takes. Now, how long does it take something to hit the floor that's dropped from this? Well, that's just an easy kinematics problem. The acceleration would be negative g, and the initial velocity is 0, and I want to know what the time would be. So that's delta y is equal to 1/2 at squared plus vit, but the vi is 0, so that's gone. So that means that our time is going to be equal to the square root of 2 delta y over a, which is the square root of 2 times 0.76 over 9.8, right? I had 2 negative signs there, they cancel out. So the square root of 2 times 0.76, 9.8, and 0.39 seconds. So that the minimum angular speed would be covering this much distance, so I guess this is the answer to part A. Minimum angular speed is if we cover 90 degrees, which would be pi over 2 radians in 0.39 seconds. And then the maximum angular speed would be covering 270 degrees, or 3 pi over 2 radians, in, of course, the same amount of time. So I just find values for those. Pi over 2 divided by 0.39. So the minimum would be about 4.0 radians per second. And then that just times 3, right? And about 12.1. So that's your range. And I guess if you think about it, like how much spin you're likely to give a piece of toast, or it's likely to acquire, maybe it makes sense that if this is the range, it's only that those small angular velocities here that would result in it not landing butter side down. And for it to make it around more than that, it would have to acquire quite a bit of angular velocity. So maybe it makes sense. Maybe this helps us understand that it's not just our lousy luck, and it's physics causing the butter side to land down. Let's see, what's next? Number 9. Rotation with constant angular acceleration. That's a little heading for these problems. If we have constant angular acceleration, it means we can use the rotational version of the kinematics equations. So here we've got a drum rotates around its central axis at an angular velocity of 12 radians per second. Sorry, 12.6 radians per second. If the drum then slows at a constant rate, so I guess that's our initial velocity, so its angular acceleration is, and it's slowing, so that would be negative 4.2 radians per second. How much time does it take, and through what angle does it rotate in coming to rest? So coming to rest would mean that the final angular velocity would be 0. So how much time does it take, and then through how much, through what angle does it rotate, right? So those, we're going to find both of those. So let's do that first. The first one is just the equation, final velocity is equal to acceleration times time plus initial velocity. So that's for part A. 0 is equal to negative 4.2 times time plus, and that's 3 seconds. That makes a lot of sense, right? If this is describing how much angular velocity it's losing every second. So if we start with this, subtract 4.2, subtract 4.2, subtract 4.2, that's just 4.2 times 3, right? So it takes 3 seconds. Part B, through what angle? So I have my choice of any equation now. I'm going to go ahead and use the one that uses the original variables that I have here. So that would be this one, I believe. Right, so 0 is equal to initial velocity squared. It's 2 times angular acceleration times the angular displacement. So let's see, that's 12.6 squared divided by 0.4. So about 18.9 radians is the angular displacement. And you could change that to degrees if you needed to, but we're going to be working mostly with radians here, so that should be good. Number 11. A disk initially rotating at 120 radians per second is slowed down with a constant angular acceleration. So again, it's slowed down, so that's negative 4 radians per second. How much time does it take the disk to stop? So stopping that's just that same problem. We just have to divide by that. So it'd be 30 seconds, right? If you start out at 120 radians per second and you take 4 off every second, it's going to take you 30 seconds to stop. That's the answer to part A. Through what angle does the disk rotate during that time? This is the same question as 9. So I'm going to do the same thing. Just write down the equation again to get used to seeing them in their angular form. So 120 squared is equal to, that's 0 plus 2 times the angular acceleration times delta theta. So 120 squared divided by 8 is 1800 radians. That's it. Number 23. What's this section? This section is called Relating the Linear and Angular Variables. So remember that if you want to know velocity, that's equal to angular velocity times r, right? And if you want to know its tangential acceleration, not to be confused with centripetal or radial acceleration, that's equal to alpha times r, right? All right, so let's see what we got here for number 23. A flywheel with a diameter of 1.2 meters, a diameter of 1.2 meters, so that means it has a radius of 0.6 meters, is rotating at an angular speed of 200 revolutions per minute. And so that's revolutions per minute, so that would be, I'd have to multiply that by 2 pi. That would be 400 pi radians per minute. And then if I wanted that in seconds, that would be 400 pi divided by 60. That would be about 20.9 radians per second. I don't know if I'm going to need that or not. I'm just practicing converting. What's the angular speed of the flywheel? That was part A. That's funny. So there it is. We did that already. The angular speed of the flywheel in radians per second, right there. What's the linear speed of a point on the rim of the flywheel? So the linear speed, that's V, is equal to omega times r, right? The further away you are from the center, the faster you'll be going. So for here, for this problem, that's radians per second times how far out are we? We're at 0.6 meters. Notice the radians just disappear. Remember, that's like a ghost unit. Radians are a ratio of a distance to a distance. So they can come and go in our conversions. So about 12.5 meters per second. You might see our meters per second and the radians disappear. And see, what constant angular acceleration in revolutions per minute squared will increase the wheel's angular speed to 1,000 revolutions per minute in 60 seconds. So you have a choice here. You can either stick with the original units or you can convert to radians per second, find the angular acceleration in radians per second, and then convert back. Or you can try to just work with these units, which might be easier in this case. So maybe I'll do, in the previous problem, I switched everything to SI units. Maybe here I'll try to stick with the original. So if I have an initial velocity of 200 revolutions per minute, we want to know about how to get to 1,000 revolutions per minute in 60 seconds, which is 1 minute, right? right? So how much would I have to increase this? Well, I'd have to increase from 200 to 1,000. So my change in angular velocity would be equal to 800, positive 800. I'm increasing by 800. And that's going to happen in the course of 1 minute. And sorry, my angular velocity is changing. I'm going from 200 revolutions per minute to 1,000 revolutions per minute. And that's a change of 800 revolutions per minute. And I need that to happen in 1 minute. So this is a case where we're talking about constant angular acceleration. So the change in velocity over change in time, this would be a straight line if you have constant acceleration. So this actual slope is equal to the angular acceleration. It's a straight line. So average and instantaneous acceleration are the same because it's constant. So there it is. It's 800 revolutions per minute. And I think that's definitely easier to do than converting. But you could do that. You could convert everything. And last, is there another part? How many revolutions does the wheel make during that 60 seconds? Let's see if we can do this. So how many revolutions does it make? Let me do this without converting. So I think we can, as long as we understand that we have to have dimensional consistency here. So as long as I stick with all my revolutions in minutes, then this should come out in revolutions. Now, just to make sure that that works, I'm going to keep all the units in here all the way through. So my final velocity is 1,000 revolutions per minute squared. That's equal to 200 revolutions per minute squared plus 2 times the angular acceleration of, did we ever find that? Yeah, sorry, that's right here, isn't it? 800 revolutions per minute times the angular displacement, but that's the angular displacement in revolutions, right? So let's just make sure that that works. And I think you can see how the units will work out here. So 1,000 squared minus 200 squared is just shy of a cool million. 96, let's say 9.6 times 10 to the 5th revolutions squared, minutes squared, right? The units get squared also. And that's going to be equal to 2 times 800 revolutions per minute squared times delta theta. And you can see when I divide this over here, everything will cancel out except for one of the revolutions. So that will give me my angular displacement in revolutions is 9.6 times 10 to the 5th divided by 1,600, which is 600 revolutions. I don't know, maybe there's another simpler way to do that. If you did find a simpler way or a different way, if you did some conversions and you did it in a more complicated way, I think it's all fair game. I would just point out, though, that if you look at what I've done here, this is how much work I'm writing out for this. If you have some tiny little scratchings, I think that this is the point in the year where the wake-up call comes that you cannot do physics that way. You cannot do physics well that way. Things get more complicated. You need to write down what you're doing, okay? Not just in case somebody else wants to come along and look at it, but for your own organization of your own thoughts, right? If you can do this problem in a tiny little space and you get a 90 or above on every assessment that I give, then that's okay. But if you get anything less than that, I think that it means that we need to practice writing things down and showing what we're doing, organizing our thoughts, blah, blah, blah. No, last one, number 25. We have here, what is the angular speed omega about the polar axis of a point on the Earth's surface that is at a latitude of 40 degrees north? So I guess first you have to know what that means. So if this is the equator, I'm just going to draw a cross-section. So if we're just looking at the side of the Earth here, being at a latitude of 40 degrees north means that you're here, right? And I know they want to know what is the angular speed, omega. Well, the angular speed of the whole Earth is the same, right, as it rotates on this axis. How far does it go? Well, the angular speed of the Earth, it makes one revolution a day. But I think maybe we would like to know what that is in SI units. So one revolution is the same as 2 pi radians, and a day is 86,400 seconds, I think. It's 3,600 times 24. Yeah, so 86,400 seconds. So the angular speed of the Earth is 2 pi over 86,400, which is 7.27 times 10 to the negative 5th radians per second. All right. And what did we want to know? Okay, so here, if you want to know the linear speed of this, linear speed is equal to omega times r. So I need to know the distance, and it's not this distance. If you're here, you're going in a circle like this. So this is the radius of that circle. So this looks like I need to do a little bit of trigonometry. And you also, if you're thinking that there's some information that you don't have here, you're right, you just need to look it up. The radius of the Earth is 6.38 times 10 to the 6th meters. Let me show you something here in your book. At the back of your book, Appendix D, I think it is. Sorry, Appendix C. You can see this. Some astronomical data. And it's got all sorts of interesting information. We'll use this a lot in chapter 13, 15, later on when we do our universal gravitation. So property, the mean radius of the Earth, I don't know if you can see it there. Our book actually uses 6.37 times 10 to the 6th. Some other books, I think of the 6.38 I must have in my head from some other place. So I'll use what our book has. I'll use 6.37. You need to know that to do this problem, right? You need to know a piece of information like that. You can just look it up. All right, so that's this. That's 40 degrees, so this would also be 40 degrees here. This would be 50 degrees. So whatever trig function you want to use to do this, to find this, the radius at of the circle at a 40-degree latitude, that's going to be equal to 6.37 times 10 to the 6th. Either times the cosine of 40 or times the sine of 50. Doesn't matter, it's the same thing. I'll do times the cosine of 40. It's the adjacent side, adjacent to that angle. So that the radius of the circle you're moving in up there in the northern latitudes is 6.37 times 10 to the 6th times the cosine of 40 degrees, and that is about 4.88 times 10 to the 6th meters. it's a smaller circle. That makes sense. So how fast are you going? Your speed, your linear speed when you're at 40 degrees latitude would be the angular speed of the Earth, which we found there, times the radius at 40 degrees, which is, I still got that number there, I'll just use that, times 7.27 minus 10 to the negative fifth. So about 355 meters per second. All right, I know it's meters per second because I have everything converted to SI units here. I think that's part A, and then part B is, what's the linear speed of the point? Oh, wait a minute, what was part A? Oh, part A, sorry. This was part A. Find the angular, and that's true for any point on the Earth, right? On a rotating body, the angular speed's the same for everything on it. That's why that angular speed is so useful. So part B, that's this. Part C, what's the angular speed for a point on the equator? It's the same as it was in part A, right? Because that's the angular speed for all points on the Earth. And part D, the V at the equator is just omega times the radius of the whole Earth, because that's the radius of your circle at the equator, which is 6.37 times 10 to the sixth times 7.27 times 10 to the negative 5. And that's about 463 meters per second. And that is the end of that assignment.